Okay, I'm going to ask for a little bit of patience, a lot of excitement, because we're going to talk about something called complexification. You've heard about simplification before, but now you're going to hear about the opposite. Actually, it's not actually related to simplifying at all, but the words are similar. Complexification. We're going to take something real. We're going to look at the complex version, and then we'll use the complex version to say something back about the real, which, if you really, no pun intended, think about it, is quite bonkers. Because complex numbers don't exist, right? Or do they? How can we use something that doesn't exist to solve something that does exist? That is mathematically very cool. So let's get into it. Remember where we're at. We're trying to find the general solution to this forced harmonic oscillator. We have sinusoidal forcing, we have damping. And we found the general solution. It was pretty quick. And we just need a particular solution. We know the form of the particular solution. We could use undetermined coefficients. We'd solve a system of equations. How much do you love solving systems of equations? I don't know. But what we could also do is look at a slightly different differential equation. So here's our differential equation. What if we look at the same left-hand side? The same left-hand side, y double prime plus 2y prime plus 2y. But instead of the right-hand side being sine of t, why not e to the it? Now notice, this is now a complex differential equation. Now, why would I do this? You'll find out more in a second, but notice we know what this is, right? We know what Euler's formula says. It says that e to the it is cosine of t plus I sine of t. So really, this is not that much different than what we had before. I mean, it's a little different, but it's not that different. So we could solve this. And actually, we're going to solve this. This is not that hard of an equation to solve. And what we notice is if we solve this, yc of t, we'll call it yc, c for complex, the complex valued solution to this complex differential equation is going to look like every complex function. It will have a real part function, and it will have an imaginary part function. And the complex valued function will just be the real function plus the imaginary number times the imaginary function. And I cannot stress this enough, just like in 3.4, the imaginary part of this function is also real. So the complex solution is a real function plus I times another real function. Why is that useful? Well, what happens if we plug in yc into our differential equation, into our complex ODE? Let's not use a question mark there. Well, what we're going to find, and I recommend pausing the video, doing some calculus, some algebra too, is remember, I is just the number. It's just a constant. When we do this, what we're going to really get is we're going to get y double prime of the real part, the second derivative of the real part, plus 2 times the first derivative of the real part, plus 2 times the real part, plus I times basically the same exact thing, but for the imaginary part, needs to equal the right-hand side. Let's rewrite the right-hand side. Why not? No pun intended again. We don't have any initial conditions yet. So the left-hand side, right, this is the left-hand side of our ODE. Right, we're just plugging it in and doing quick little calculus. And the right-hand side is going to be e to the it, which again we know is cosine of t plus I sine of t. This is the right-hand side. This is the same right-hand side. So if this is a solution, and we know our solution looks like this, then this equation must hold always. Complex numbers and complex functions are only equal if their real parts are equal and their complex parts are, and their imaginary parts are equal. So what does that tell us? Must be true. Well, we know two things. We know that the real part must equal the real part. So we know the real part y double prime plus 2y real part prime plus 2 times the real part of y needs to equal the real part of this, which is just cosine of t. And we know the same thing holds for the imaginary parts. That must equal the imaginary part here, and the imaginary part from Euler's formula is just sine of t. Now, why do we care about this? You may recognize the second equation. This is exactly the differential equation we're trying to solve. Is it not? Yeah, it is. So, if we could find the solution to this differential equation, and don't worry, this is not going to be bad. Finding a particular solution, and again, I should really specify, this is just one particular solution. We're not looking at general solutions right now. If we're looking at, if we can just find one particular solution to this differential equation, and we definitely can, it's not bad at all, then the imaginary part of that is going to solve our differential equation. And remember, the imaginary part of a complex number or a complex valued function is real. And that's going to have a few advantages. We're going to do it first, and then I'll show you the advantages. But again, we have to deal with some more complex analysis, so it requires a higher level of mathematical understanding to do this, but there's going to be multiple advantages. And again, we'll talk about those at the end of the video. For now, let's do it. All right, let's solve. What we're going to do is we're going to solve the, let me be a little bit more precise. First, we're going to find a particular solution to our complex ODE. And then we're going to say, hey, the imaginary part of that solves or gives a particular solution to our original ODE, our original real ODE. So let's do that. We're going to go over here and solve this complex value differential equation. So let's copy it down again. Y double prime plus 2y prime plus 2y equals e to the it. How do we find a particular solution to this? We guess. And this is where things are nice, because we no longer have a system of equations when we guess, because the right-hand side is just an exponential function. Sure, it's an exponential function with a complex coefficient, but that's fine. We know how to deal with that. We have Euler's formula. So let's guess. We're going to guess that our solution, because we just need one. We just need a particular solution. We already found a homogeneous solution. We just need one. And so what we're going to guess is that our complex valued function is just some number e to the it. Now here's the bad news. There's a little bad news. What do you think this number is? Do you think this number is guaranteed to be real? No, it could be complex. And yeah, most of the time it will be. I guess literally it will always be complex. Because if you think, because the real numbers are technically a subset of the complex numbers. So every real number is also a complex number, just with the zero imaginary part, if you want to be pedantic. So if we guess this, how do we use the guessing method? We take the derivative, we make it equal. So the left-hand side is going to be the second derivative of this, which with the chain rule, derivative of an exponential function, this I comes down twice. So, oh my gosh, my cat is right about to lay on my keyboard. So when the left-hand side just becomes I squared times a e to the it plus 2 times the first derivative, which is I a e to the it plus 2 times the original function AE to the IT, and that needs to equal the right-hand side. But before we make it equal to the right-hand side, let's clean this up. This just becomes negative AE to the IT. This doesn't really simplify. And then we have a positive 2AE to the IT. Okay, we're pretty close. We can combine these. Minus 1A plus 2A is going to give us 1A e to the IT, plus I'm going to write it like this, I times 2A e to the IT. So now there's good news and bad news here. Okay, so we need this to equal. And actually, I want to rewrite this a little bit, because notice what we're trying to make it equal. We're trying to make it equal e to the IT. So instead of writing it as real part plus I times the complex part, let's actually just factor out an e to the IT instead. I'm going to kind of change my mind. So you could get rid of this step if you want, or you could just rewrite it. If we factor out an e to the IT, what do we get? A plus 2A I. What do we want? We want this to equal 1. Because if this is equal to 1, then we equal the right-hand side. So when does that happen? Let's go off to the side. When does A plus 2AI equal 1? Well, we can factor out an A. That's when 1 plus 2I times A equals 1. Or when A is 1 over 1 plus 2I. So this is our value of A, but this is not really a simplified, useful form for a complex number. Complex numbers are much easier to work with if it's just in the form A plus BI, real part plus I times the imaginary part. So if you remember back, or maybe you never learned this, I don't know, how do we simplify this complex number? It's just like rationalizing the denominator. Because I is a square root of -1. How would we rationalize the denominator if we had a square root down here and a binomial term? We'd multiply by the conjugate on the top and the bottom. So the top becomes 1 minus 2i. The bottom is the difference of squares. That's 1 minus 4i squared. That's 1 plus 4. That's 5. We found our particular solution to the complex version of our differential equation. So we have YC. That's great. So YC of t is A, which is 1/5 minus 2/5 times I. It's A e to the IT, just like we guessed. Now, you're probably really upset with me right now. You're like, Jason, this is a lot of work. Could we not have just solved the system of equations? Because we're not even done yet. Have a little faith, have a little trust. We will see the advantages to this method. Because what were we doing? We said, okay, look, we could look at this complex ODE and notice that the imaginary part of our complex valued particular solution is going to be a solution to what we need. So we found YC, and we noticed that the imaginary part is going to solve our original differential equation. So we just need the imaginary part of this, and that'll be our particular solution right here. So let's do that. What's the imaginary part of this? Oh, well, it's not obvious. It's not obvious because we have this e to the IT, but don't worry. It's just one Euler's formula and a little simplification away. So we could rewrite this as 1/5 minus 2/5 I. This just becomes cosine of t plus I sine of t. Now I'm going to do things in a little shortcut. You could FOIL this all out and be very careful, and I would love that. But I'm just going to rewrite this as real part plus imaginary part. Real part is 1/5 cosine of t. And then it's going to be plus 2/5 sine of t. Why? Because this is part of the real part, And this is part of the real part. I squared is -1. And then plus I times the imaginary part, which is going to be 1/5 sine of t. Plus, I actually don't know if it's a plus. What's the other one? Minus 2/5 cosine of t. So this is our complex solution. And that, of course, has a real part as a function of t. And it has an imaginary part as a function of t. And again, remember, the imaginary part is real. So we found the complex solution. The imaginary part solves our original differential equation because the original differential equation was sine. If the original differential equation had cosine, we'd be looking at the real part. So our particular solution is just the imaginary part, 1/5 sine of t minus 2/5 cosine of t, which is cool. And again, it's really not that useful yet. Where were we way back? I told you could have just guessed a cosine b, or a cosine t plus b sine of t. We already know how to do this. And it was annoying. It's a system of equations, but it's not hard. We could have found this yp much easier, to be honest. And we do notice it's in the right form, a sine t plus b cosine t. And yeah, you would have found a as 1/5. You would have found b as -2/5. However, using complexification and creating a complex differential equation and finding a complex solution and then using that complex solution to find our real valued particular solution. And again, we haven't actually written the general solution yet, but doing all of this have some advantages. And again, you're still just taking that on faith. We'll talk. I should finish the problem though. Let's actually go back and finish the problem. We have our particular solution. Remember, we already found our homogeneous solution. That was k1 e to the negative t cosine t plus k2 e to the negative t sine t. And so remember that by the extended linearity principle, the general solution to the forced or non-homogeneous differential equation is going to be the sum of these two. So our full solution to the original differential equation that we looked at, that forced harmonic oscillator with sinusoidal forcing, is going to be k1 e to the negative t cosine of t plus k2 e to the negative t sine of t plus 1/5 sine of t minus 2/5 sine of t, cosine. That is our general solution. Any forced harmonic oscillator will look like this if it has that forcing function. And what K1 and K2 will be depends on the initial condition. And again, we could see a lot of things. We'll do more analysis of this later in this section, but we can see things. Right? Here's the natural response. Here's how this would behave if there was no forcing function. The natural response dies out. This is an underdamped harmonic oscillator, just like we said. This part's dying out, leaving the forced response. This is saying eventually it's just going to look like this. And that's very common for these forced harmonic oscillators. It's always going to happen because 0, 0 is always in equilibrium for the homogeneous differential equation. Okay, so where am I at? Let's finally answer the question. And again, it's only going to be half the answer. The other half of the answer is in the next video. Why did we do this? The question you are all asking, I'm sure. And there's a few reasons. So one kind of lame reason, but maybe you like it, is there's no system of equations this way. Right? That's an advantage. We didn't have to solve a system of equations. It's kind of a lame reason, though, I'll be honest. Other things is better qualitative analysis. Certainly we can do some qualitative analysis right now, but the next couple videos do a lot more qualitative analysis. It's so much that we actually split it up into 2 videos. And wait a minute, maybe I should have split up into 3 videos. It's split up into, I don't know how many videos it's split up into. But we're going to be able to do some really cool things, because again, if you look at what this function really is, and this is a slightly different function, but if you have a cosine function plus a sine function, the graph of that is just a sine function or just a cosine function, right? If you have the same period of a sine and a cosine and you add them together, it's just a sine or a cosine. Sine and cosine are the same function. They're just shifted versions of each other. So what we're going to be able to do with this complex analysis is, among many other things, is we're going to be able to rewrite, and don't freak out. This is fine. We're going to be able to rewrite this into just a single function. We can see that this cosine function I've graphed is the exact same function. We can easily see the amplitude of the cosine function. We cannot easily see the amplitude of this function. So if this was our forced response, we would not know the amplitude by looking at it. Here we can immediately tell the amplitude. Also, we can very quickly find the phase shift. Oh, this is a cosine function shifted left a certain amount. And we can find out exactly how much left or right this cosine function shifted. From the graph, we can see it shifted right about 0.3, which is about half of this arctangent. But anyway, we'll talk about where this arctangent comes from. Don't worry, there's very minimal trig. It's not that much trig that's coming. Yeah, that's some cool stuff. So that's another reason why this complexification is useful. It really does let us do some more powerful complex analysis. It'll, and I kind of got into this already, but it's going to be helpful. It's going to be better for analyzing amplitudes and phase shifts. In fact, I remember when I first learned about this, or maybe I should say when I first remembered learning about this, is I was like, wait, what is the amplitude of this? I know this is just one function. This is just one sine function or one cosine function. What is the amplitude? And I guessed, and my guess was right. We'll talk about where that is. But it's actually the length of that vector, of the coefficient vector. If the x component's 1/5 and the y component's -2/5, the amplitude of the resulting sine or cosine vector is just the length of that total vector. We'll talk about why that is in the next video. Okay. And again, you know, these are the good things, but there's a very obvious con of you do need some complex analysis. We have complex numbers. Maybe that makes you sad. Complex numbers are very cool, but you know, sometimes they can be hard. Or tricky, depending on what your experience is. They're not inherently worse. Just, you know, if you're not familiar with them, it's going to be a little harder. So the next couple of videos are really where we show all the cool things that we can do by analyzing this with complex numbers, and really talk about some fun, powerful things. We got cool visualizations as well, but that is where we're at right now. Anyway, hope you enjoyed it. We got more cool stuff where we really see why this is awesome in the next couple videos. Bye-bye.